So we've seen two examples of greedy algorithms in the last two segments. As for dynamic programming, the example problems we show you are not necessarily important in themselves. They are particular problems. But the hope is that by seeing a few examples, you will get the general pattern of how one designs and proves correct greedy algorithms. However, the third example of greedy algorithms we're going to see is actually important as a problem by itself. It's the Huffman coding problem for file compression, which is a hugely important operation when we send files around on the internet. So what happens when you transmit a file or a video or anything else on the internet? Well, the representation of the file or the video might be very large. There might be lots and lots of bits underlying the representation. So what we might like to do is to compress this file before transmitting, because that way the file gets to the other end faster, it uses less bandwidth, it has all kinds of good properties. So one of the goals that we want to think about is, one of the problems we want to think about is data compression in general. So we will take a particular angle on this, and what we will produce is an algorithm called Huffman Coding, which is an example of a greedy algorithm. And although it's a specific example, Huffman coding is actually used quite often, and it's an important algorithm. Okay. Just to give you a more concrete sense of the problem, let's imagine that we're transmitting English text over the internet. So the symbols are the usual ones: A through Z, lowercase, uppercase, punctuation marks, spaces, carriage returns or new lines, and so on. So you have the sequence of characters that you want to transmit over the internet. So you want to take a file containing the sequence of characters. Of course, everything on a computer is done, as you know, as zeros and ones. So you want to encode each symbol in this alphabet. The alphabet, again, you're familiar with the English alphabet. So each symbol in this alphabet should be encoded as a string of zeros and ones, so that when you're actually transmitting a word, you would transmit the binary code for each symbol in that word. Or when you're transmitting a file, you transmit the binary code for each symbol in that file. Okay? And we would like to minimize the total number of bits we're sending, or the length of the sequence of bits we're sending. That's what we want to minimize. The obvious idea that I hope occurs to you after a few moments' thought is that you want to use very short code words for symbols that are frequent. In English, typically the symbols of the letters E, R, and T are very frequent. There are others that are almost as frequent, but these are probably the most frequent letters. So you would like to use really short code words for these, because you'll be using them repeatedly in the file you're sending. And use longer code words for letters like Z or Z and Q. But say you decide to do that, and let's just try one particular way of encoding the symbols of the alphabet. We might say, let A map to the sequence 0, 1, 0, B map to the, and F map to the sequence 0, 1, 0, 1, and G map to the sequence 1, 1, 1, 0, and S map to 1, 1, 0. This is just a random example of how you might code letters into binary strings. The problem if you use this particular code is, suppose at the receiving end you receive the sequence 0, 1, 0, 1, 1, 1, 0. Well, that sequence could actually stand for two combinations of two letters. So one combination is the combination where the first three bits are interpreted as an A, 0, 1, 0 is the code for A, and the last four bits are interpreted as G, 1, 1, 1, 0. Or you could break it up this way as 0, 1, 0, 1. The first four bits represent an F, and the last three bits represent an S. The problem is this is ambiguous. Someone receiving the sequence of bits, the 7-bit sequence, will not know if you sent AG or FS. We want to avoid this kind of ambiguity. And one way to avoid this kind of ambiguity is to insist that no letter's code word should be a prefix of another letter's code word. In this case, what happened was that the code word for A, 0, 1, 0, is a prefix of the code word for F, 0, 1, 0, 1. So that was the problem. And so we should make sure that no letter's code word is the prefix of another letter's code word. If we can do that, then we won't have this ambiguity. All right, so such codes should really be called prefix-free codes because there are no code words that are prefixes of any other. But because of historical convention, they're actually called prefix codes rather than prefix-free codes. Okay, so let's talk about prefix codes. So here's an example, a very small alphabet consisting of just the letters A, B, and C. By the way, we use the letter capital sigma, Greek letter capital sigma, to denote an alphabet usually. That's a common letter for denoting alphabets. For each symbol x in sigma, let f of x be the frequency of x, the number of times it occurs, or if you like, you can normalize the frequencies and call it the probability of occurrence of the letter x in the file that you're transmitting. And let d of x be the length of the encoding of x. So what is the length of the encoding of x? Well, if we're going to talk about prefix-free codes or prefix codes, we can represent the entire coding of the alphabet as a binary tree. How's that? Well, you start at the root, make the left branch have label 0 and the right branch have label 1. All the code words, all the symbols whose code words start with the symbol 0 will be in the left subtree, and all the symbols whose code words start with the symbol 1 will be in the right subtree. So if you're going to use this particular prefix-free code, A goes to 1, B goes to 0, 0, and C goes to 0, 1, that code word would be represented by having A be in the right subtree because it starts with 1. The other two symbols, B and C, start with 0. The code words start with 0, and they're in the left subtree. And if you follow the path down to the leaf marked B, the labels on the edges are 0 and 0. So that's 0, 0, and that is the code word for B. Similarly, the code word for C is obtained by following the path from 0 to 1, from the root to C, and you see that the path has labels 0 and 1. So you can see that a prefix code can always be represented by a binary tree where the symbols of the original alphabet, the English alphabet, occur at the leaves of the tree. These are the leaves of the tree. So the symbols for the original alphabet occur at the leaves, and the length of the code word for a particular symbol is the depth of that leaf. For example, the length of the code word for B is just the depth. I mean, how far, what is the length of the path from the root to that leaf B? It's length 2, so that's the depth of B, and that's going to be the length of the code word for B. So what's the overall length of the coded file that you're going to transmit? Well, each symbol occurs with a certain probability or frequency. The symbol x occurs with this frequency f of x. Every time it occurs, you need to send a code word whose length is equal to the depth of x in this tree. And so the total length of the binary string that you transmit is going to be the product over all the symbols of their depth times the frequency. And the idea of data compression or Huffman coding is to minimize this product. Minimize the summation over the symbols in the alphabet of their depth times their frequency. So that's really saying, I mean, roughly speaking, that conforms to the intuition that you want to put very frequent symbols near the root so their depth is small. So let's make some greedy attempts at solving this problem. So for example, here's a very greedy idea, following up on that intuition. Let's take the really most frequent symbol we're given and give it a code word of length 1. That's the smallest length you can have for a code word. Let's just code it up as the string 0. Now recursively find code words for the remaining symbols. Of course, all the remaining symbols now have to have code words beginning with the letter 1. Why? But with the bit 1. Why is that? Because this code is supposed to be prefix free. You cannot begin another code word with the letters, with the symbol, with the bit 0 if A has been encoded as 0. So continuing this manner, so if you're given an alphabet A, B, C, D with the frequencies, A has a 0.26 frequency, B has frequency 0.255, C has frequency 0.245, and D has frequency 0.24. A is most frequent, so we give it the symbol 0. So the remaining code words must all begin with 1, so they're all in the right subtree of the root. So all the remaining symbols here must be in the right subtree of the root. And Out of those, B is the most frequent, so let's give it the symbol 0 now, the bit 0 now. So B gets this bit 0 here. It was already got a 1 before. Gets the bit 0 and continue on this way. So you get this particular tree. And if you look at it, the cost of this tree, which is measured as the product, as a summation over all the symbols of the product of their frequency and their depth, is about 2.2. Instead, if we had just actually made a balanced tree like this, where all code words were length 2, so A was encoded with the string 00, B was encoded with the string 01, and so on, this would have, of course, the solution would have cost 2, because every code word has cost 2, so the solution also would have cost 2. Okay, so the cost would be 2 there. So one attempt would be to say that let's follow this idea in general. Let's just ignore the frequencies of different symbols and just make every code word be of the same length if possible. So basically, how much length do you need? You need a length that's the logarithm base 2 of the number of symbols in your alphabet sigma. So if the alphabet had 4 symbols in it, you need every code word to be length 2. So why not just make every code word of length 2? Would that be a good optimum solution? Well, that doesn't work very well when the frequencies are very lopsided. For example, if the first symbol, A, has frequency 1/2, B has a frequency 1/4, C has frequency 1/8, and D has frequency 1/8, this balanced tree has cost 2 again, because every code word has cost 2. But if you use this unbalanced tree on the left-hand side, this tree here, then the cost is only 1.75. So we find that, in fact, in this case, we should have chosen the unbalanced tree, whereas in the first case, the balanced tree was better. So neither one of these attempts seems to solve the problem all the time, and we want a greedy approach that will, in fact, solve the problem on all inputs. So the correct algorithm takes the following idea. The greedy idea would be to take the 2 symbols that occur with the least frequency and combine them to make a new symbol. So basically treat them as though they're one new symbol whose frequency is the sum of the frequencies of the 2 symbols with the least frequency, and recurse on this problem, which now has only n-1 symbols. Originally we had n symbols. We just combined 2 symbols and replaced them by 1, so we have n-1 symbols, and we can keep going like this. So the greedy algorithm is to recursively and repeatedly combine the 2 symbols of least frequency. So in this example here, what we are given 5 symbols. The 2 least frequent symbols are D and E. We just broke a tie between D and C arbitrarily. So D and E are the 2 least frequent symbols. And what we're going to do is we're going to recursively solve the problem on 4 symbols where we've replaced D and E by a new symbol, let's call it Z1, whose frequency is now the sum of these 2, which is 0.275. Once we solve the problem recursively, we'll build a tree for these 4 symbols. And when we've got the tree, we look at the leaf that contains Z1, and we'll replace it by this picture. We'll replace it by a new node with 2 children, D and E. So that is going to be the idea of the Huffman algorithm, which we will describe in detail in the next segment.